Okay, hello. We are the Vectorized Acoustic Deterrence of Elephants Research Group. This is our ECE NCSU capstone project called the Wall of Sound. Team leads are Arpod and myself. Team members are Grayson, Noaf, and Morgan. We are sponsored by the Army Research Office, who we have been in direct contact with Paul Reed. The mentors for this project, who we give special thanks to, is Dr. Pitts, Dr. Gupta, and Dr. Shifley.
So a little background about what our project is actually trying to tackle. The problem is human-elephant conflict. So in sub-Saharan Africa, also in Eastern Africa and India, there's a lot of loss of life and livelihood caused by elephants raiding crops. And as a result, humans can die and be trampled. Elephants can also die when they're trying to defend their crops. And and just a statistic that was kind of baffling was over 500,000 individuals in India alone every year are affected by elephant crop raiding. So this is a problem that we're actually trying to tackle, and the Army Research Office has been trying this for a couple of years, and this wall of sound is one of the ideas that we came up with.
Yeah, so the previous ARO solutions to this problem have been e-collars that give the elephant a negative stimulus, which acts as a deterrent system, versus the RFID tag alert system and the infrasound detection system act as alert systems to let the people know that there's an elephant in the area. Similar to our project, they have also tested a LRAD, or long-range acoustic device, and that basically leads into our project is aiming to create this acoustic fence or wall of sound idea to deter elephants from farmland. So a quick overview of our project is that we were required to test the efficacy of this wall of sound idea, and we went about this by designing a test bench, and this test bench should be able to broadcast sounds within the range of elephant hearing, with the hopes of playing sounds that are known to deter elephants without causing any physical harm or psychological harm. The challenges with this have been achieving directional sound, emitting longer distances in this fence-like manner, playing desirable sounds, and desirable sounds are ones, hopefully that will tackle this elephant habituation problem, and then just a multitude of other acoustic barriers. So our intention for this design is to have these hexagonal stack of speakers, basically, that will transmit sound. The idea is that the elephant will come into this between these, basically, and will not want to pass through it. And if you see in the bottom picture, there's a perimeter, so the elephants can't approach from any angle and come in. Okay, this is our final design overview. We're using the idea that a higher frequency sound wave will become more directional, so we're using these ultrasonic transducers at 40 kilohertz, and that high frequency carrier wave is going to have an envelope of our audio signal. And so the idea is that it will hit a hard or dense surface, shed the high frequency carrier, and reflect back only the audio. We're achieving this with a PCB stack where the top one has our transducers on it, and the bottom one has our amplifiers, which has customizable filters, gain, and other parameters that are adjustable. That is being fed by a digital to analog converter, and that's going to give our amplifier array its audio signal. The power is received by an Ethernet cable, which will have a plus 30, minus 30, and ground rail. And then each of the surrounding hexagonal PCBs will be sharing the power and audio signal. The digital analog converter will be fed by a computer PC, which is running our MATLAB script, which just has a simple GUI interface, and that has a lot of adjustable parameters. We'll go into that later.
Okay, so we went through many different design iterations. So during the course of this project, we had different milestone demonstrations called alpha and beta demonstration. As you can see, we've progressed significantly, where our alpha and beta demonstration, we were able to design PCBs, but in our pre-alpha demonstration, we only used just these solderless components to actually test what it sounded like. So So during our pre-alpha demonstration, this was done in the winter of 2020 at the end of our first semester, where we had the idea for this what's called a parametric array, which uses these ultrasonic transducers to emit directional sound, as Hunter was mentioning. And we were using an analog mixer, a low voltage audio amplifier in order to accomplish this. But the sound that we were receiving was very heavily distorted. It was not at nearly the volume that we wanted, but it was progress. It worked. So what we figured out is in order to make it louder, we need better amplifiers. So instead of using this low voltage audio amplifier, we just opted for regular power amplifiers, redesigned the whole circuit for that. And as well, you can see we're using a computer power supply. We opted just to use a benchtop power supply to achieve higher voltages. And in addition, we needed to change the ratio of amplifier to transducer ratio. Over here, we only had one amplifier per 20 transducers. And yeah, you can see it was very messy test bench. But then if you go to the next slide, we can see that in our alpha demonstration, we were actually able to design and print a bunch of PCBs, and we accomplished a lot. So you can see instead of inputting the sound just with a computer, we decided to opt for a little microcontroller that can actually read a sound off of a SD card. It goes into this analog mixer, which then does the modulation. It then amplifies it, sends it over to the transducer array, and it sounds great. However, one thing that we realized was this problem with hysteresis, which, if you're not familiar with what that is, hysteresis is essentially this time-dependent problem that there's magnetization within these components. So, like, for example, what we were seeing was the volume at a certain frequency was a certain amount, but when we swept it, swept the frequency up and then back down, it was actually a different amount when we came back, and this caused a lot of inconsistencies with our results, which we didn't want. We want to be more consistent. So we found out this hysteresis problem was actually the analog multiplier. So we decided to get rid of that.
So for the beta demonstration, we decided to remove this multiplier and we replaced it with essentially a DAC. And this, lets us do a lot of stuff digitally, which we'll get into that later, how that works out better for us. Another thing we changed here was adding a female Ethernet port. So now instead of having to probe for power, we can simply plug in an Ethernet. There's no issue. We didn't end up adjusting the amplifiers here in any way. Yeah, and this completely solved our hysteresis issue. What was coming out of this DAC is what the rest of the system basically deals with.
All right, so this is our final design. As you can see, we had these modules of the speakers stacked vertically to emulate this quote-unquote wall of sound. However, we're going to show later on that the reason why we chose them to be hexagons is so they can be modular, so we can make them any shape in reality. And as Hunter mentioned, we have this nice power over Ethernet with this Ethernet housing at the bottom. Just simply plug it in, powers, and the power shared across all of them. And then we also have this aux cord, which comes from the laptop and the DAC, which shares the signal on what to emit through all of them. And what was good is that in the amplifier PCB, we were able to implement a variable like jumping in and out different filters and different types of gains where we can adjust the parameters of the incoming signal for the parametric array. And as you're going to see in the next slide, we also have this very simple MATLAB interface on how we can actually modulate the sound. So over here, kind of skipped over it, but essentially you just select the audio file. You can select different modulation techniques, which I'm going to briefly mention in the next slide. And essentially, the MATLAB just automatically modulates it, and then you can export it. And then when you actually have the sound, you can just play it just straight up from your laptop, and then it will emit nicely on the parametric array. So if you go to the next slide. So some of the different modulation techniques we were looking at, there were many papers about parametric arrays and how to decrease total harmonic distortion and what's called intermodular distortion. And of all these different modulation techniques, the main thing to take away is that these two different papers, one was selecting different modulation techniques and sweeping them across frequency, whereas other ones were sweeping them across what's called a modulation index. And using both of these, we were able to hone down on what was the most optimal modulation technique that we wanted to use for our demonstrations. However, there's still a lot more research to be done on what's the best for us and how we can just improve sound quality at the end.
So here is a quick setup for how we test this device. So we're using actually a benchtop power supply, which is the reason we decided on this power over Ethernet, because it's as simple as plugging this power supply in here, and then you don't really have to touch this thing again once it's set up, which is nice. So that is the female Ethernet housing we're plugging into. And so we will take an Ethernet cord, and that will go into the female housing connected to the power supply, and then to the board. And that is carrying plus and minus 30 volts and our ground signal. Okay, and then we have a single auxiliary port which will go in, and the power and signal, audio signal, will be shared across all those boards. And that's going to plug into our 192 kilohertz stack, which will go into our PC, and the system is fully ready to use at that point. And then here's a brief video on how the modularity aspect works. These transducers pop off for any kind of repairs or swapping that may need to happen or rearrangement. There's a single plug on the back. It goes back on pretty easily. And then as RPod is showing, these guys can connect together. They fit together super well, and provided there's an amplifier board also connected, these can go in any arrangement. And then this just shows our single input power and single input signal, which only goes to the one master module. And then here's a little bit more about the modularity. As you can see, we have a minus voltage, plus voltage, our signal, and then our common rail. For our prototype, these were just soldered together, but in the future, we would like for these entire boards to be moved, and I'll talk a little bit more about that in a bit. And then here is an outdoor demonstration we did. And please notice that the volume is the same coming from the computer.
So that was using a standard modulation technique, 600 hertz. You can barely hear anything on the side, but when the cameraman was in front of it, sounded much better. This is standard modulation, but with a song. And then to show the different distortion, we played a piano song. And one thing to note about that is that the what we're using to film it and the microphone that picked it up, it sounds completely different than what it is in person, but there's significantly less distortion when we use that modified amplitude modulation technique in the second piano song. But there's a trade-off between how loud the output is versus how distorted it is. So we need to optimize for that. And we also tested in an anechoic chamber as well as outside to get radiation patterns to see how directional our device was. So this is the radiation pattern for 200 hertz tone using standard amplitude modulation. This radiation pattern is plotted in decibel volts, which is what the microphone picked up. And we didn't find the need to test behind the device because it was essentially silent. But you can see that that there's this one large lobe at 0 degrees, and the at the sides is like basically completely silent at -80 decibel volts. And then we up the frequency to 600 hertz, and as you can see, the lobe is much more prominent. It decreases on the sides, as you can see from the 200 hertz, and it becomes much more directional. But as a result, we have more prominence in the 30 and the 330-degree lobes. And we increase this yet again to 1500 hertz. And you can see the 30 and 330 lobes are very pronounced, as well as the 0 1. And then at the side, it's like you can see the side, it completely decreases. So this is like very directional, but much more, I don't even know how to say this, but the lobes are much more also prominent. And but this was very low resolution. We were only testing this using we were just writing down different values. So we wanted a higher resolution radiation pattern. So what we did is we walked uniformly in a semicircle in front of our device and recorded audio and tried to walk at a steady pace. So this is prone to human error, but you can see that the lobes at the 30 and the 330 degrees, as well as one large lobe at 0, and the at the side it's basically quiet, which is very good results.
Okay, so moving forward with this project, we would like to re-implement an audio sound shield like we had previously, this time with a faster sampling rate so our system can basically run. We would need 192 kilohertz for that. And that also helps us with this random audio playing, and that's going to help for the preventing the elephant habituation. And that leads us to testing on elephants. Perhaps we could, set this thing up around some food or something of that nature, just to see what kind of deterring effects that it has on elephants. We'd also like to test more physical modularity, perhaps a click into place system rather than any soldering, because right now our transducers are pretty modular, but the amplifier boards themselves are not very modular. And then there's significantly more research on theory, and the whole purpose of this testbed was to test those things.
So some of the more research that we want to do in the future, or that can be continued with this project, was one, improving the sound quality. Like I mentioned, with the different modulation techniques, there's a lot of ideas that we have in terms of different ways on how to modulate it, both or primarily digitally, and then also with signal processing, where we can use analog signal processing, more filters, analog filters, but also on the digital side of things. And then also we want to help improve the directionality of the sound. Right now it's pretty directional, as you can see with those radiation patterns. However, we've thought of potential ideas like phasing, which we can have a focus point that this device kind of focuses on and kind of narrows everything down a little bit. And also there's a lot more ultrasonic phenomena that we are not familiar with for both the sound quality and directionality that we want to do a lot more reading on, and would need more acoustic research in that. And then as for measurements that we did with like the radiation pattern to get results, there's a lot of work to be done on that, because the microphone can have interference with this 40 kilohertz carrier. It's called like sporadic sounds, and we don't want that because that changes our measurements. So some of the options we've seen are like using acoustic film for the microphone, using different types of microphones, different types of testing configurations. So that would be nice to test. And then also in terms of getting different results, three-dimensional radiation pattern or a more high resolution and a more consistent way of measuring these radiation patterns would be very effective.
Okay, and that's all we have for this project. We thank you guys for listening and your attention. If you guys have any questions at all, please send either RPod or myself an email. At the email address is there. Another thing I would like to mention is that video that we played earlier of the sound will be linked in the comments for a higher quality version of. All right, thanks.